Hi all, I welcome you all to the next lecture today. Here Professor Ravi Kumar, School of Mechanical Engineering, Sastad Interview University. Today I'm going to start about re-entry vehicles and re-entry heating particularly. So previous to this lecture, you have been given a clear idea about orbital mechanics, right? Followed by the introduction to the satellites and its application. Today we'll see how actually re-entry happens and what are the consequences of re-entry and what are the different forces which will be encountered on an on a re-entry vehicle, right, and how to avoid that, and a particular emphasis will be given on re-entry heating and how to avoid that. So let's start our topic for today. So first is how actually things have started. The successful exploration of space requires a system that will reliably transport payload such as personal and instrumental etc. into space and return them back to Earth without subjecting them an uncomfortable or hazardous environment. So this is a requirement, right, particularly expected from a successful spacecraft. So, in other words, we can say the spacecraft and its payloads have to be recovered safely into the Earth. So, we have seen the re-entry capsules and winged space vehicle approach the Earth following by the safe landing. So, you might have seen several examples, right, in the Hollywood movies as well as in real time scenario where re-entry into the Earth atmosphere have been accomplished. And also, you might have seen that was famous example, right, in 2003, right, and Kalpana Chawla incidents, right, when that space shuttle or was entering into the Earth atmosphere and it was exploded because of the phenomena called re-entry heating. It was not able to sustain that heat and it has brought into the two parts. One part gone into the space, another part came on the Earth. That phenomena may happen, but after that incident, right, lot of researchers have come up with significant solutions to avoid the aerodynamic heating. Still aerodynamic heating or re-entry heating is a subject of research. Lot of research is going on. So in order to understand this aerodynamic heating, the researchers must have in-depth understanding of high speed aerodynamics. So lot of parametric studies need to be done before come to a conclusion of fully optimized design for space exploration. So if you look at the history of space exploration just started immediately after the World War II in 1960s. Russia started the space race, and after that, it is still continuing, and the coming future warfare and all necessary things will be dominated by the space shuttles, right? And to accomplish that, and to understand the space, you need a spacecraft. So re-entry systems were among the first technologies developed in 1960s for military photo reconnaissance, life science, and manned space flights. By 1970s, it led to the development of new space shuttles. Today, if we look at today, space technology has developed to space planes which intend to go and come back regularly from Earth to space stations. If we look at the example, particularly European Space Agency Hornets and Japan's Hope, these spacecraft are designed to land like an conventional aircraft on the airport. As I said that spacecraft, if we look at the configuration of a spacecraft, it will be similar like an aircraft and it has to be launched with the help of a launching vehicle, and launching vehicle will be a rocket. With the help of that, we used to send the spacecraft into the outer space. When it's going to be land, it will be landing with help of its own engine. So it is fitted with the engine. So when it's going to be land on the Earth surface, it will be landing like an aircraft after after crossing all those aerodynamic heating stages and finally land on the Earth. So, as I mentioned that, ESA, Hermes, right, and Japan's Hope, these are particularly two famous spacecraft which were particularly designed to land on the airport like an aircraft. So, if you look at the Hermes was basically a joint venture. It was not a single country which was working on the Hermes project. So, Hermes spacecraft is the result of decade-long collaboration between NASA, European Space Agency, Roscom, Russian, and Japan Aerospace Exploration Agency, and ISRO, our Indian. So they are planning basically to develop it soon, right, for space exploration, particularly from Earth to Mars orbit and return back. So, first, Hermes project was started by the French Centre National company in 1975. Later, it was taken by the European Space Agency. So, it was basically being designed, taken into consideration that space travel should be very easy and convenient. At any time, you can go to the space, explore, and return back. So in coming future, it will come into the effect. So this collaborative work is going to be end by 2029. So we are expecting that by 2029 we will be ready with the future spacecraft known as HARMS. Next one is Japan Hopes. Particularly, Hope was Japanese experimental space plane project designed by partnership between National Aerospace Space Development Agency and National Aerospace Laboratory of Japan. Now it is known as basically JAXA, JAXA, JAXA. JAXA is nothing but Japan Aerospace Exploration Agency. So these two agencies basically combinedly known as now JAXA. So it was positions for most of its lifetime as one of the main Japanese contribution to the International Space Station. Another being Japanese experimental module. The project was eventually cancelled in 2003, by which point test flights of subscale tested had been successfully conducted. So they have conducted the flight test and as well as real time test, but it has been shut down in 2003, and after that no more work has been done. But these were designed particularly to land on the conventional airports. From any airports, right, they can land. So, return back to the topic again. As I said that for accomplishing a successful exploration to space, we need a spacecraft. Now, spacecraft need to be designed in such a way that it should encounter all the forces which will come in its way, like aerodynamic heating, re-entry heating, and atmospheric turbulence as well. So, for entering into the atmospheric and non-atmospheric planet, the problem involves is reducing the spacecraft speed. How to reduce the speed? Because in the outer space, there is no resistance. When there is no resistance, the motion which have been provided to it will be remain almost same. It is very difficult to reduce the speed. How to do that? That is a big question in front of a scientist and researcher. So they are looking for the solution for it. Another big problem is aerodynamic heating. How to minimize that? We cannot completely avoid it, but we can minimize it. For that, lot of work has been done. We are having thermal shield system, or we can use thermal barrier coating, special coating at the nose to avoid the re-entry heating. But still, some more modifications are possible and need to be done. So if you look at what is basically re-entry vehicle, if somebody asks you what is re-entry vehicle, a re-entry vehicle could be a rocket, could be a satellite, or can be a manned capsule. So when returning to the Earth or when landing on the another planet, a safe re-entry through the atmosphere is needed. So safe re-entry can be difficult because of the very high speed of this spacecraft, which creates very high temperature when entering through the Earth atmosphere. So engineers need to be find ways for the spacecraft to survive these very high temperature environments. So this is a famous example of the manned capsule NASA Orion re-entry vehicle. So in front of researchers, these are the big problems: how to survive the re-entry heating. And for that, a lot of modifications has been done. Still, a lot of research is going on. So forces acting on re-entry vehicle (AP) categorize the forces which will come on the way of re-entry vehicle. They can be classified into three major forces. One is gravitational force acting towards the center of planet from where it is getting entered into the Earth atmosphere. So now question will arise whether in space gravitational force is there in some zone, there is some value of gravitational force, right? Gravitational force maybe 1 by 6, 1 by 9. So that gravitational force will pulling the spacecraft back to the planet, right? That need to be countered. So gravitational force acting towards the center of planet. Next one is gas dynamic force opposite to the direction of motion of vehicle, and gas dynamic forces will come because of the presence of shock waves, right, at the surface of the spacecraft. Third force, centrifugal and gas dynamic lift force acting normal to the direction of motion of vehicle, that will also try to change the flight path of the re-entry vehicles. So these are the major three forces which would be acting on the surface of re-entry vehicles and need to be encountered. And for encountering these forces, you need sufficient power, right, powerful engine to counter these forces. If we talk about the entry corridor, there is only particular, passage through which only re-entry is possible. You cannot do re-entry in any way of going from in space to the Earth. So there is only a particular thin zone through which only re-entry is possible. Successful re-entry is possible. Otherwise, what will happen if you are going this side? There will be too much drag. If your space vehicle is going to counter too much drag, and due to drag, what will happen? Lot of heating of the surface may happen, and if it is too very high drag, chances of damage to the vehicle is also possible, and which will lead to the accident, right? If you are going away from this corridor here, deceleration will be too much low. You may not be able to cross the magnetic field of the Earth atmosphere. All right. So there is only particular thin zone, right, through which only successful re-entry is possible. So outer zone, if you look at the boundaries of these, one is called overshoot boundary and is called undershoot boundary. So these are the maximum minimum condition, right, up to which you can re-enter into the Earth atmosphere, or you can do the entry into the planet. So an entry corridor is a range of entry conditions within which an entry is possible. Undershoot boundary and overshoot boundary forms the upper and lower limits of the entry corridor, as clearly mentioned here. So this is the big problem, basically. So you have to go through only these very narrow zone. So terrestrial flights are tolerant of guidance error accompanied by landing approach. There may be some guidance error. So an undershoot may cause destruction of vehicle during entry, and an undershoot may result in harmless exit to the space. So if you are going this side, right, then it is very difficult, very difficult, right? No, undershoot is there. If you are going this side, it is very difficult to enter into the Earth atmosphere. So you will be still in a space, and if you are too much away from it, right, this may cause the structural damage to the vehicle during re-entry. So if the guidance error results in excessive undershoot, right, these are the undershoot, these are the excessive condition. You look at this and this, these are the too much excessive condition. If due to guidance error, if excessive undershoot happens, the vehicle will enter into atmosphere at an excessively steep angle, thereby experiencing too much deceleration. If the guidance error results in excessive overshoot, similar if you are going this side also, because of the guidance error, if you are going to the excessive overshoot, in that case, vehicle will not slow down considerably in order to complete entry in a single pass. So speed cannot be reduced. That is also very difficult, right? Particularly to complete re-entry in a single pass, it has to be reduced. So in both the condition, right, either excessive undershoot and excessive overshoot are not recommended. Hence, the shaded portion represents excessively overshoot and undershoot are excluded. So there is only particular thin zone which is showing here through which a successful entry is possible, and that is known as entry corridor. Entry corridor. Now, when we talk about the re-entry heating, this is the major concern of space vehicle when they are entering into the Earth atmosphere, and how to survive that is a big challenge. So, a vehicle approaching the Earth or a planetary atmosphere from space or from orbit possesses a large amount of kinetic energy due to its speed and potential energy by virtue of its position. So these energies have to be dissipated and converted into heat to decelerate the vehicle to zero velocity and altitude. So from a speed of 8 km per second to energy per mass of 31.4 megajoule per kilogram must be dissipated. So this much amount of heat need to be dissipated, then only you can slow down the vehicles required for re-entry. So at high speed associated with re-entry from space, air cannot flow out of the way of the onrushing spacecraft fast enough. So when the vehicle encounters the atmosphere, a shock wave will form ahead of the nose of vehicle, hitting the atmosphere in this zone to a very high temperature. The moment it comes in contact with the atmosphere, Earth atmosphere, a shock wave will form in front of the nose, will cause very high temperature rise. As the vehicle plunges into deeper and denser atmosphere, the vehicle will increasingly be heated by the atmosphere. Why? By developing the layer of incandescent atmosphere around it, while the speed of vehicle will continuously be reduced by braking force of the atmosphere. In this manner, the vehicle's kinetic energy is converted into heat. If all the vehicle's kinetic energy were converted into heat within the vehicle itself, it would be more than enough to vaporize the vehicle. That condition should not be existing. That's why I said that aerodynamic heating is a big challenge and we need to avoid it. We need to minimize it. Otherwise, very difficult to enter into the Earth atmosphere. So there are basically two ways in which total energy is dissipated from vehicle. First, by waves, unloading major part of the heat on the atmosphere by shock waves, right? So you design your front nose of vehicle in such a way that shock should not attach over it. It should be detached shock, so that you will have a sufficient spacing, right, between the shock and your vehicle. So it will not be direct heating of the surface, so a lot of heat will get dissipated to the atmosphere. Second method is to radiate heat away from hot surface of the vehicle. So how basically this will happen? You look at this example, right? This is the space vehicle which is entering, and this is condition of red hot, right? This atmosphere means complete material is becoming red hot. The movement is entering into the Earth atmosphere, and this is the formation of shock waves. So usually for the spacecraft, we make nose as a blunt nose, right, to avoid the formation of attached shock. If there is no attached shock, there will be no large aerodynamic heating. To avoid the large aerodynamic heating, it is a bluff body, right? Bluff nose. In that case, shock will form a distance away from it. In that case, In that case, the surface of the vehicle will be subjected to less heating. So the diversion of heat by strong shock wave is the result of molecular interaction in the gas around the vehicle. When molecules strike the forward surface, they bounce back. So many of the rebounding particles collide with the oncoming molecules, diverting them from the surface and preventing them by hitting it by direct impact. A blunt nose produces the strong shock wave. Since the fraction of the total heat load that is transferred is directly proportional to the strength of the shock wave, the stronger the shock wave, lesser will be the heating on the surface. That means one shock wave has formed here. So when flow coming, molecules will strike over the surface and rebound back. When they are going back, they will disturb the motion of oncoming molecules, right? So they will not be directly hitting on the surface. Because of that, surface will be shaped from the direct heating. They will be dissipating back. So higher the strength of the shock wave, lower will be the aerodynamic heating of the surface. Higher the strength of the bow shock. We used to say that as a detached shock or bow shock. That's why for a space vehicle, we make the front nose as a blunt nose. Right? If it is a blunt nose, in that case, a shock, normal shock, strong detached shock will form, right? Detached shock will be a formation of, means a combination of one strong normal shock followed by two oblique shock. Oblique shock will have lesser strength compared to the normal shock. So immediately after the normal shock, flow will become subsonic. When flow is subsonic, there will be no aerodynamic heating. That's why blunt nose is preferable. And this aerodynamic heating is a big concern, right? Particularly we have to deal with. We have to deal with. So this is regarding the re-entry vehicle, right, and aerodynamic heating. So with this, I want to close the today discussion, right? If you are having any doubt in this, feel free to write in the comment section, or you can directly ask to me. So as a summary, today you have been introduced about the re-entry vehicle. What are the re-entry vehicles, and what are the big challenges of re-entry? You have been given a clear idea about entry corridor. There is a particular passage through which only re-entry is possible, right? Successful re-entry is possible. Otherwise, if you are going either downside or upside of it, right, upper boundaries or lower boundaries of it, vehicle will face a lot of problems, and re-entry will become difficult or almost impossible. And finally, you have given a clear idea about aerodynamic re-entry heating, how it is going to impact over the spacecraft, and also you have been given a clear idea about how to minimize it. We cannot avoid the aerodynamic heating, but you can minimize. There are various methods. In some of the spacecraft, we are using the thermal protection system, that is called thermal shield. So front nose will be made by the special material, so that will be attached as a thermal shield at the nose. Or some space vehicles, we are using even a thermal barrier coating to avoid the aerodynamic heating. And most of the space vehicle front nose, if you look at, or spacecraft front nose, if you look at, that will be blunt nose. It is having a more like a circular cylinder. So due to which, what will happen when it interacts, right, the Earth atmosphere at hypersonic speed, right, there will be formation of shock wave, and shock wave will be a detached shock wave, and we prefer to have detached shock wave in order to minimize the aerodynamic heating. So if it is a detached shock wave, airflow will not have direct interaction over the boundaries, right, or you can say within the boundary layer. So within the boundary layer, heating will be less compared to the outside of the boundary layer. So outside atmosphere of boundary layer will be get heated, but near the surface heating will be less, and your surface will be safe from any kind of adverse temperature conditions, and that need to be uh, you know done when you are entering into the earth atmosphere. Otherwise, it will be very disastrous, particularly when you are entering doing the re-entry into the earth atmosphere. So still this aerodynamic heating or re-entry heating is a subject of research. Lot of research is going on, but we have come up with some significant methods to avoid it and are being used. So this much is enough for today, right? Go through it. If you are having any doubt, feel free to contact me. We'll meet you again. I will meet you again with a new topic in next class. Have a nice day. Good day.